this works. So stoichiometry is just an extension of a math skill that you have already learned how to do. Okay. It's a math skill that is an extension of mole conversions. And we've spent a lot of time with mole conversions over the past, I don't know, couple of units. And so like this is just an extension. But in order to really talk about it, I want to go back in time and review a couple of things. So in the past, we said that with mole conversions, we could go from mass to mole, and we could go to particles, right? Okay. And so when we would go from mass to moles, does anybody remember where we would get the information for that? Correct. We would use the molar mass off of the periodic table. So molar mass. And we would go from moles to particles. Where would we get that information? Not quite on the periodic table this time. It was 6.02 times 10 to the 23rd, which you may have written on your periodic table. But so that was mole conversions, and you may recall doing those not too long ago. Now, in stoichiometry, what we're going to do is we are going to take the idea of mole conversions and we are going to convert from one substance to another substance in a chemical equation. So that might look something like this. So we can go from mass to mole, and then we're going to go to another mole, and then we're going to go to something and then we're going to go to mass again. Now, when we go mass to mole, just like up above, we are going to use the molar mass, and that would come from the periodic table. And when we go from mole to mass, we would be using the molar mass. And that would also come from the periodic table. But when we would go from mole to mole, we're going to use something called the mole ratio. And so what's actually happening here is we are going to go potentially from mass of substance A to mole of substance A to mole of substance B to mass of substance B. The math skill is something that you've already learned. We're just kind of linking it together. So we're going to use this new flow chart, mass to mole to mole to mass, to be able to solve problems in this unit. So the other thing that's important to understand is that every single chemical reaction, every single stoichiometry problem starts with a chemical reaction. And in order for us to go ahead and work through the chemical reaction to use stoichiometry, we're going to have to balance this chemical reaction first. So on the reactant side, I have potassium and nitrogen, and on the product side, I also have potassium and nitrogen. On the reactant side, I have 1 potassium and 2 nitrogens, and on the product side, I have 3 potassiums and 1 nitrogen. When I go to balance this equation, I'm going to go and try to balance my potassiums by putting a coefficient of 3 here, which will give me 3 potassiums on both sides. I now need to balance my nitrogen, so I'm going to put a coefficient of 2 here, which will give me 2 nitrogens, but it's going to give me 6 potassiums. So that means I have to go back and change this to a 6, and now this is balanced. So what I'm going to do is I'm going to clean this up. I'm going to rewrite it so that it looks a little cleaner for us. So I have K solid plus N2, which is a gas, reacts to form K3N, which is a solid. Now, 6, 1, and 2. Now, what I want to get at here, and some things that are really important to understand, is that the coefficients in a balanced chemical equation are equal to the moles of that substance in the reaction. So the coefficients in the balanced chemical equation are equal to the number of moles of those substances. So what I'm getting at here is that I can now create what's called a mole ratio between any substance in a balanced chemical equation. So for example, if I was comparing potassium to potassium nitrate or nitride, my mole ratio would be something like 6 moles of potassium for every 2 moles of potassium nitride. If I was going to compare, say, potassium to nitrogen, my mole ratio could be 6 moles of potassium for every 1 mole of nitrogen. And if I wanted to compare moles of nitrogen to moles of potassium nitride, I would have 1 mole of nitrogen for every 2 moles of potassium nitride. So in this one single equation, there are up to 3 different mole ratios. Does that make a little bit of sense so far? Now, the easiest way for me to try to explain how all of this works in terms of the math associated with this would be for me to simply do a few examples. So let's start with the smallest example. So in this problem, I'm given that I have 12.5 moles of potassium, and I'm asked to convert it to moles of potassium nitride. So this problem is telling me that I'm going to go from moles of potassium to moles of potassium nitride. And when I go from mole to mole, according to this flow chart that I had up above, I need to use something called the mole ratio. So I'm going to write that here so I don't forget. Mole ratio. Now, the mole ratio in this equation is the relationship between potassium and potassium nitride. So if I'm looking at potassium and I'm going to compare it to potassium nitride, I can see that for 6 moles of potassium, I can produce 2 moles of potassium nitride. Now, that gives me enough information to actually solve this problem because I now have my mole ratio. So I'm going to take my given, which is 12.5 moles of potassium, put it over 1, and I'm going to go moles of potassium to moles of potassium nitride. And when I do that, I need to set it up so that the moles of potassium cancel out. So I'm going to put moles potassium on the bottom and moles of potassium nitride on the top. Now, the value would be 2 moles of potassium nitride for every 6 moles of potassium. So I'm going to go and calculate. I'm going to take 12.5 times 2, which is 25, divided by 6, which is something like 4.166666667, something like that. And now we need to go ahead and assess significant figures. So in this problem, I draw my arrow and I count 1, 2, 3. So I have 3 sig figs. And then the other thing that I want to make a point of here is that technically the mole ratio is going to have infinite sig figs. The mole ratio values are going to have infinite sig figs. Now, one of the things that we didn't really talk about in the first semester is that if the number is a statement of fact or it's a counted value, then that would have infinite sig figs. So, for example, when I balance this chemical equation 6, 1, and 2, that's a statement of fact that's undeniable. I can't balance it any other way. And because I can't balance it any other way, that means that the number of significant figures that is in the 6 moles of potassium or 2 moles of potassium nitride is infinite, and we don't really have to worry about it. So when I go to identify how many sig figs I need to have in my answer here, I count to 3. I see that 6 can round that 6 up. So my final answer is going to be 4.17 moles of potassium nitride. Now, hopefully that doesn't seem too incredibly awful, but we'll try it again. So here's my balanced chemical equation. And in this problem, we are asked to convert 0.425 moles of potassium to moles of nitrogen. So this tells me that I'm going to go from moles of potassium to moles of nitrogen. And so that means that I'm going to be comparing potassium and nitrogen in this reaction. So I am going to be using my mole ratio again. And when I use my mole ratio this time, the relationship is simply going to be 6 moles of potassium for every 1 mole of nitrogen. And so now again, because I only need the mole ratio for this style of problem, I'm going to go and I can now start solving my problem. So I'm going to take the 0.425 moles of potassium, put it over 1, and I'm going to set my mole ratio up so that moles of potassium cancels out. So I put moles of potassium on the bottom, and I'm going to put moles of nitrogen on the top. The relationship is 1 mole of nitrogen gets used for every 6 moles of potassium that are used up. So when I go to do this problem, I can simply multiply straight across. So 0.425 times 1 divided by 6, and I get something like 0.0708333333. Again, I'm going to count sig figs. So I'm going to draw that arrow and count 1, 2, 3. So I have 3 sig figs here. In my mole ratio, those have infinite sig figs. So I'm going to draw this arrow here. I get to that 7, and I get 1, 2, 3. That 3 cannot round the 8 up, so my final answer is going to be 0.0708 moles of nitrogen.
So why? Oh wait. So it would be 3 plus the 0 in pound.
The 0 is not significant, correct?
Okay.
So now we're going to take this skill and we're just gonna ratchet it up 1 level, which hopefully isn't too bad. So in this problem, we are told that we have 6.23 grams of nitrogen and we're going to convert it to moles of potassium. So according to the mole flow chart that I drew earlier today, we are going to go from mass of nitrogen to moles of nitrogen to moles of potassium. Now, as you may recall, when you go from mass to moles of anything, we need to use the molar mass from the periodic table. So I'm going to write that down so I don't forget. Molar mass. And when we go mole to mole, what we've been already doing is we've been using the mole ratio. So the easiest thing for me to find in this problem, I think, is the mole ratio. So I'm going to look at the two things we're comparing, which in this case is nitrogen, and we're comparing potassium. So in this case, my mole ratio is 1 mole of nitrogen for every 6 moles of potassium. We also need to calculate the molar mass of nitrogen in this case, which this one won't be too bad. So we have 2 nitrogens times the mass of nitrogen, remember from the periodic table, which is 14.01, which gives us 28.02 grams per mole of nitrogen. And I am purposefully writing it this way to show that the relationship between the molar mass is 1 mole of any compound is equal to its combined mass on the periodic table. So when I set this up, I'm going to take what I've been given, which in this case is 26.3 grams of nitrogen, put it over 1. And I'm going to go mass to moles to moles. When I go mass to moles to moles, or when I go mass to moles, I'm going to use my molar mass, and I'm going to set it up so my mass, my grams of nitrogen is on the bottom, and the moles of nitrogen is on the top. Here I have 1 mole of nitrogen for every 28.02 grams of nitrogen, which I'm going to change that color. At this point, I can convert moles of nitrogen to moles of potassium using the mole ratio. And my mole ratio this time I'm going to set up so moles of nitrogen is on the bottom, so I can cancel it out, and moles of potassium is on the top, so that's what I end up with. I have 6 moles of potassium for every 1 mole of nitrogen. So I'm going to use my calculator. 26.3 times 6, get an answer, divided by 28.02. I get another answer, and in this case, my value that I get is something like 5.631691649. Got to go and assess significant figures, so I draw that arrow, and it's 1, 2, 3 sig figs. Draw an arrow down here is 1, 2, 3, 4 sig figs. And I'm going to remember that my mole ratio values have infinite sig figs, so I don't really worry about them. So this problem has 3 sig figs is the fewest, so I'm going to draw an arrow and count 1, 2, 3. I'm going to see that 1 will not round that 3 up, so my final answer here is going to be 5.63 moles of potassium. So now we've gone mole to mole. We've gone mass to mole to mole. Now we're going to do one more example. Well, a couple more examples, but really we're going to go from moles. So we're going to convert 1 mole of potassium nitride and we're going to convert it to grams of potassium itself. So this problem is going to simply be moles of potassium nitride to moles of potassium to mass of potassium. When we go mole to mole, hopefully you're getting comfortable with the idea that we're using something called the mole ratio. And we go mole to mass, we're using the molar mass from the periodic table. So I'm going to go ahead and figure out what my mole ratio is. And so when I go to figure out what my mole ratio is, I'm going to start by identifying what I'm supposed to compare. So I've got potassium nitride, and I'm going to be comparing it to potassium. So my mole ratio over here is going to be 2 moles of potassium nitride for every 6 moles of potassium. Now, the other thing that we need for this problem is the molar mass of potassium. And so I know that I have 1 potassium times its mass in the periodic table, which is 39.10 grams, which will give me 39.10 grams of potassium in 1 mole of potassium. Again, the molar mass is always equal to the mass in the periodic table in 1 mole. So I'm going to take my given, which is 1.254 moles of potassium nitride, and I'm going to go mole to mass. When I go mole to mole, I'm going to use the mole ratio, and when I'm using my mole ratio, I'm going to set it up so my moles of K3N cancel out, so they go on the bottom. My moles of potassium are going to go on top. The relationship is 6 moles of potassium for every 2 moles of potassium nitride. Now I'm going to use the molar mass here, and I want my moles to cancel out. So I'm going to have moles of potassium on the bottom and grams of potassium on the top. This is going to be 39.10 grams of potassium over 1 mole. That is so ugly, it's bothering me. That's better. Okay. Now, when I plug this into my calculator, I'm going to take 1.254 times 6 times 39.10. That answer ultimately divided by 2. So in this problem, I'm going to get like 147.0942. Again, we're going to assess significant figures. So I'm going to draw that arrow and count 1, 2, 3, 4. So that's 4 sig figs. My mole ratio has infinite sig figs. And my molar mass has, let's see, draw the arrow and count 1, 2, 3, 4. So that's 4 sig figs. So my final answer is going to have 4 sig figs. So I'm going to draw this arrow and I'm going to count 1, 2, 3, 4. This 9 will round that 0 up. So my final answer here is going to end up being 147.1 grams of potassium. Woo! Hopefully this feels like kind of a review of stuff we've already done. 2 more examples, but a new balanced chemical equation. So here we go. In this chemical equation, I have zinc, I have bromine, I have silver, and I have nitrate because it shows NO3 shows up on both sides. So I have 1 zinc, 2 bromines, 1 silver, 1 nitrate. I have 1 zinc, 2 nitrates, 1 silver, and 1 bromine. Starting to balance, going from left to right, my zincs are balanced. I'm going to leave them alone. My bromines are not. I have 1 on the left and I have 2 on the reactants and 1 on the product side. So I'm going to put a coefficient of 2 there, which will give me 2 silvers and 2 bromines. I'm going to put a coefficient of 2 in front of my silver, which will give me my 2 silvers, and I've already got 2 bromines. So this one happens to be balanced 1, 2, 1, 2. So we're going to use this new chemical equation to work through the longer of these two types of problems. But it's not that much longer. It's just got to keep track of some stuff. So in this example, we are going to be converting 45 grams of silver nitrate to grams of zinc bromide. So in this problem, we are going to go from mass of silver nitrate to moles of silver nitrate to moles of zinc bromide to mass of zinc bromide. When we go mass to mole, we're going to use the molar mass. When we go mole to mole, we're going to use the mole ratio. And when we go mole to mass, we're going to use the molar mass. So that tells me that I've got to do 3 things here. I have to determine the molar mass of silver nitrate. I have to determine the mole ratio between silver nitrate and zinc bromide. And I have to determine the molar mass of zinc bromide. So there's 3 things I have to do before I can calculate the answer here. So I'm going to start by figuring out my mole ratio because that seems like the easiest thing for me to do. So I'm going to be comparing silver nitrate to zinc bromide. So in this instance, I have 2 moles of silver nitrate for every 1 mole of zinc bromide. Now, the other things that I have to do is I have to calculate the molar mass of silver nitrate. So I see that I have 1 silver times the mass of silver, which is 107.87 grams. I have 1 nitrogen times the mass of nitrogen. And I have 3 oxygens times the mass of oxygen. And I'm just going to simply add them together. 107.87 plus 14.01 plus 48. It'd help if I added right. So 107.87 plus 14.01 plus 48. That's much better. It's going to give me 169.88 grams of AgNO3 in 1 mole. I also have to calculate the molar mass of zinc bromide. So we'll do that now. So I have 1 zinc times the mass of zinc, which is 65.39. I have 2 bromines times the mass of bromine, which is 79.90, which is 159.80 grams of bromine. Add that up. And I get something like 225.19 grams of zinc bromide in 1 mole. So now I'm going to set my problem up using my given as my starting point. So I'm going to take 45 grams of silver nitrate, put it over 1, and I'm going to go mass to mole to mole to mass. So I'm going to use the molar mass for silver nitrate, and I'm going to put grams of AgNO3 on the bottom and moles of AgNO3 on the top. We said that 1 mole of AgNO3 is equal to 169.88 grams of AgNO3, mass to mole. Now we're going to go mole to mole, and we go mole to mole, we're going to use our mole ratio, and we're going to set our mole ratio up so that silver nitrate cancels out. So I'm going to put moles of silver nitrate on the bottom and moles of zinc bromide on the top. The ratio is 1 mole of zinc bromide for every 2 moles of silver nitrate. And then we're going to go mole to mass. And when I do that, I'm going to use my molar mass for zinc bromide. But at first, I'm going to put moles of zinc bromide on the bottom and grams of zinc bromide on the top. So there are 225.19 grams of zinc bromide in 1 mole of zinc bromide. Now I'm just going to use my calculator and calculate this out. So 45 times 225.19 divided by 169.88 and eventually divided by 2. So this problem, I get something like 29.825622. Got to assess significant figures. This is 2 sig figs. This is 1, 2, 3, 4, 5 sig figs. These are infinite sig figs. And this last molar mass over here is 1, 2, 3, 4, 5 sig figs. So my final answer is going to end up with 2 sig figs. So I'm going to draw this arrow. I'm going to count 1, 2. I'm going to see that this 8 can round the 9 up. But when it does that, it makes it 30. And you need a fat decimal point right there. Grams of zinc bromide. Hopefully this isn't feeling too incredibly awful. I know this is really riveting stuff to do on a Monday afternoon when it's allegedly 57 degrees outside. Allegedly. But hey, we got one more. And I have faith that you can do this one more on your own. It's very similar to the one we just did. And I want you to give it the old GHS try. So go ahead and try example number 6. So hopefully, as you're working your way through this, some of you are done, some of you are still working. You noted that you had to go from mass to mole to mole to mass, zinc bromide to silver bromide. You found the mole ratio to be 1 mole of zinc bromide to 2 moles of silver bromide. You calculated the molar mass of zinc bromide to be 225.19 grams in 1 mole of zinc bromide. You calculated the molar mass of silver bromide to be 187.77 grams in 1 mole of silver bromide. You set this problem up so mass of zinc bromide canceled out, moles of zinc bromide canceled out, moles of silver bromide canceled out, and then lastly, you were left with grams of silver bromide. And then you multiplied straight across the top and then eventually divided, identified you needed 4 significant figures, and hopefully you got 17.09 grams of silver bromide. So that's the final type of problem that you will see in this type of in what's called stoichiometry. So no homework this evening. We will practice this in class tomorrow. Anybody have any questions? No? Okay. Have a good afternoon.